Why is IIR filter stability critical in electrical design? Have you ever wondered why stability in infinite impulse response filters is so important in electrical engineering? Let's break it down in a way that makes sense. Stability in these filters ensures that when you input a signal, the output remains controlled and predictable. This property is known as bounded input, bounded output stability. If a filter is unstable, the output can spiral out of control, leading to distortion or even system failure. That is something no engineer wants to deal with. Now, what sets IIR filters apart from finite impulse response filters? IIR filters use feedback elements in their design, which means their response can theoretically continue indefinitely. This feedback is represented by poles in the filter's transfer function. The position of these poles in the complex Z-plane is what determines whether the filter is stable. For stability, all poles must be located strictly inside the unit circle. If any pole lies outside this boundary, the output will diverge over time, which is not acceptable in practical applications. From a design standpoint, keeping these poles inside the unit circle is essential. It guarantees that the filter's impulse response stays bounded, allowing the system to behave in a predictable manner. This stability is directly tied to the filter's region of convergence, which must include the unit circle for the filter to be causal and stable. In practical terms, stable IIR filters are often preferred in many signal processing applications. They can achieve sharp frequency response characteristics while using fewer coefficients, making them less computationally intensive than their finite impulse response counterparts. However, the feedback nature of IIR filters makes them sensitive to coefficient quantization and finite word length effects in digital implementations. If not managed carefully, these factors can shift poles outside the unit circle and lead to instability. In summary, the stability of IIR filters is vital in electrical design because it ensures that outputs remain bounded for any given input. This stability preserves the integrity of signal processing tasks and prevents unwanted behaviors like oscillations. By ensuring that poles stay within the unit circle, engineers can create reliable and effective filter designs that meet the demands of modern applications.